All right, good morning, everyone. Welcome to our lecture today. Today we will be talking about Mars. Before we do that, I just wanted to let you know we have a new homework assignment due. It looks like I forgot to put the due dates on both of these things. This reading assignment is due Friday, so that would be for 8, I believe. And this homework assignment is due next Wednesday. That will be a week from today. And so that is the 15th, I believe. Put a little question mark there. I'm not 100% sure on that one. I'll just write next Wednesday there. All right. So I don't have any other further announcements. So let's go ahead and begin. I'll start today with a thought question. So, early public interest in Mars was dominated by the observations of what features? Let's go ahead and push pause and think about this for a moment. All right, it turns out that the correct answer is B, canals. Although this was a mistranslation. So one of the first people to write about this was Schiaparelli. And that was in 1877. And he was Italian and he used the word canale, which actually translates to channels. By having them written as or translated to canal, it was sort of interpreted as being some sort of non-natural feature, i.e. made by Martians. And so in popular culture, there was a lot of talk of Martians and Martian civilizations and whatnot. So moving on to a little more modern view of Mars. We did have some early space exploration of Mars, but in the last 20 years or so, we have sent a lot of space missions to Mars. Some of these are orbiters, some are landers. Some in particular that I want to draw your attention to here. One is Maven. I talked about this yesterday. Spirit, Opportunity, and Curiosity, these rovers, we've learned a lot from them. Maven in particular is important. That's studying the loss of Mars's atmosphere. So very important for astrobiology. There are currently 5 orbiters and 2 rovers actively surveying and exploring Mars. So this is one of the most studied bodies in the solar system after the Earth and the Moon. Huge potential for life. Our nearest neighbor. A lot of what's done here is called comparative planetology, where we're comparing Earth and the current state of Earth and the evolution of Earth to Mars, the current state of Mars and the evolution of Mars. So why are these two bodies end up so differently? What do we think is the same about them? We can learn a lot by comparing the two. So let's look at some data from Mars, or really some, basic Mars data. So a couple of things I want to point out to you. This first one here is the mass. This is much smaller than Earth. It's about 1/10 of the mass. So some important things that happened because of this. It cooled faster, leading to a thicker mantle. Its crust, its mantle is much thicker than Earth's, much stronger, can support larger mountains. It has less gravity, so those mountains can get bigger. It also has more trouble holding on to an atmosphere. It has no magnetic field because of this. So this cooling faster has had a huge effect on it. Another thing I would like to point out here is the atmospheric composition. You can see that it's about 95% carbon dioxide, which is a greenhouse gas. Despite that, it's still much colder and drier than Earth. You can see down here that its average temperature is minus 50 degrees C, so much, much colder than Earth. It's very cold. So you might ask, if it has so much greenhouse gas, why is it much cooler than Earth? And a lot of this has to do with these low atmospheric pressures here. So this atmosphere overall, very little atmosphere. It's about 1% of Earth's atmosphere. Now, I keep saying that we have very little, or it has a lot of CO2. Now, compared to what? If we look at Earth's atmosphere in comparison, we have about 78% N2, nitrogen, about 21% O2, oxygen, and our carbon dioxide is about 0.04%. And that's mostly because of the carbon dioxide cycle, where the atmospheric carbon dioxide on Earth, because of all the water, gets dissolved into the oceans and then eventually trapped into rocks and minerals down inside the Earth. So even though it has a high percentage of greenhouse gases, it is very, very cold. All right. So here's a thought question along these lines. The Martian atmosphere has a much higher level of CO2 than Earth's atmosphere, despite the high levels of greenhouse. Why is Mars much colder? So see if you can get the right answer here. I just talked about some of this on the previous slide. Go ahead and push pause if you need to. All right, so the main reason here is the density of Mars's atmosphere. If you have less atmosphere, that equals less of a greenhouse effect. Okay, so these other things are true. Mars has no water or very little water. So that is true. Mars is much smaller and has a lower surface gravity, and its semi-major axis is bigger, and so it is farther from the sun. So it's not that those A, B, and C aren't true. It's just that they are not the reason it is colder. All right, moving on. Oops. Looks like we missed a slide there. So looking at Martian seasons. So the first thing I'll say about this is they're more extreme than Earth. And this is due to a couple of things here. The orbit is more elliptical, so that it is sometimes very close to the sun and sometimes very far from the sun. So much more elliptical than Earth's orbit. I don't have that number off the top of my head, but there's about a 50 million kilometer difference between these two edges. It's about a 20%, or sorry, about a 25% difference between here and here. All right, so it also has a larger axial tilt. So about 25, oops, sorry, not percent, 25 degrees, where Earth's is about 23.5 degrees. So again, this leads to larger seasonal variations. One thing we can see here is when it's close to the sun, this is during the northern winter because the North Pole is pointed away from the sun here. You can see that by this axis arrow here, the North Pole's pointing away from the sun. And also remember, because of Kepler's laws, it's moving faster here and slower there because planet moves faster when it's closest to the sun and slower when it's farther away. That's Kepler's second law about equal areas and equal times. So what it means is that during this part of the year, we get mild winters in the northern hemisphere and short, hot summers in the southern hemisphere. And if we look at the other end of the orbit, where the planet is moving slower, here we end up with long, cool summers in the northern hemisphere and long, cold winter in the southern hemisphere. Now, what that does is it drives some global weather where the atmosphere freezes out. Remember that atmosphere is mostly CO2. It freezes out on the poles. So we get these large polar ice caps that are made of CO2. And we can see a big extreme here going from the late winter in the north, where we have a relatively large ice cap here. We have quite a bit of CO2 frozen out, to a very small ice cap here in the summertime, where that gets that CO2 goes back into the atmosphere. That means that they have big global windstorms. Lots of dust here. So because of these large seasonal changes, large amounts of atmosphere being frozen out and then evaporated, it ends up with, like I said, big global windstorms. So there's large variations in the polar ice caps between winter and summer, mostly due to these two things: the elliptical orbit and the large axial tilt. All right, so that was some sort of seasonal features of Mars, a little bit about its atmosphere. Let's look at some of the geology here on Mars. So this is a topographic map of Mars. This is the elevation here, going higher and lower. The color scheme, so these northern regions up here, let me move to a little bit different color so we can see that better. Maybe a nice purple, and I'll make the pen a little bigger. This region up here, you can see, is relatively low. It has very few craters. So this is called the northern, let me get a different pen for that. Northern lowlands. And that is a relatively young surface, and we know that by the numbers of craters on there. At one point, this might have been a global ocean. So an ancient global ocean, maybe that's why there's no craters. At one point it was filled up with water. You can even see, it's hard to on this picture, but there are river valleys, especially in this region here, that are show looks like there was at one time water flowing from the highlands down into the lowlands. And so it may be that whatever craters were there, ancient craters were filled in with silt and whatnot, resurfaced due to erosion, that types of things. So that corresponds down here to this recent Amazonian time, lightly cratered northern plains and slopes. So that's region 3. That's up here. The other main region that we have, I'll do that one in green with a little bigger pen, is down here. This whole region, more or less, we'll call that region 2. And that corresponds down here to the middle, the Hesperian time period, moderately cratered. Oh, sorry. I made a mistake there. That is not region 2. That is region 1. That's this early, heavily cratered. And again, we know that was formed early on. There's lots of craters. The more craters a surface has, the older it is. Now, there's sort of an intermediate region here. And this is often referred to as the Southern Highlands. Now the last part here is sort of this region, maybe here. This part here is region 2, and that's the moderately cratered terrain south of Tharsis. And Tharsis is this region right here with these 5 huge volcanoes. So this is the Tharsis Bulge. They call it the bulge because you can see here that whole region is raised up. It's all in this red color here. The neighboring regions are either green or yellow, which are lower than that. And this has 4 large volcanoes. One of them being Olympus Mons, the largest volcano in the solar system. So let's take a quick look at that. So here is a picture of Olympus Mons from the top. That's this volcano here. You can see in this diagram that it is much, much taller than Everest, or even the Big Island of Hawaii, which is actually the largest mountain on Earth, but most of it is submerged beneath the ocean. So very, very tall mountain. So it is the largest volcano in the solar system. A big, huge shield volcano. It's called Olympus Mons. And we can see that it's much taller and wider than Everest. Much taller and wider than any mountain we have here on Earth. Another striking large feature, and this is what Schiaparelli was looking at before, or at least looking at earlier. This is Valles Marineris, the Mariner Valley, and this is as far as I know, the largest canyon in the solar system. It's about the length of the United States, and it is about 4 times deeper than the Grand Canyon. One interesting feature of that is that we can see sedimentary rocks in the walls of this canyon. Now, we think that this canyon is probably built through tectonic activity, unlike the Grand Canyon, which was carved out by a river. Maybe this is some kind of rift valley, but we don't think there was any plate tectonics on Mars, which is usually the cause of rift valleys. It's fairly near the Tharsis Bulge, so it may be formed a large crack because of the uplifting of the Tharsis Bulge. Sometimes these cracks can form on other planets, not this large, but other cracks can form as the core contracts and as it cools, and then the outside layers crack up. So nobody really knows how this valley formed, but it's pretty interesting to look at. All right, so a little writing prompt here for you, thinking about why was Olympus Mons able to grow so large? So I'll let you stop, pause the video, and think about that for a little bit. All right, so the answer to this is really three main things. And I mentioned a few of these earlier. The thick crust of Mars allows for large mountains because it can support them. The thicker your foundation, the thicker your crust, the taller your mountain is here. On Earth, our crust is only so thick, and it's floating on top of some liquid magma, and so if we build mountains too large here on Earth, the crust just tends to sink down and the mountains don't get any taller. The next thing would be no plate tectonics, so that the hole, the crack, whatever this lava was flowing out of, has been sitting in the same place for a very, very long time. You can think back to the when we talked about the Hawaiian Islands and how they are a hot spot and the crust is moving over that hot spot, and so you end up with a whole chain of volcanoes, and that you can't build one too tall. So the hot spot is always in the same place. Now, it looks like this volcano is dormant. It isn't still active, but when it was forming, that hot spot was sitting in one place, dumping all of its lava there. Now, the last one is related to the size of Mars, and that Mars has weak gravity. So it's easier to build upward. And this is related to the strength of the crust. If the mountain's lighter, you can support a bigger mountain without the crust collapsing underneath it. So those are the three reasons why Olympus Mons is the largest volcano in the solar system. Now, I know I had assigned some reading and some videos on water on Mars. We're going to be talking a lot about the history of Mars, atmosphere, and water on Mars on Friday, and so I didn't want to make this lecture too long, so I'm going to include that information about the water on Mars and the history of the water on Mars in Friday's lecture. So there'll also be a little bit of additional reading, so please check that out on Canvas, and have a great day. Be safe out there. Take care of yourselves.